Okay, so we're on our second video for section 4.6, where hopefully we can learn how to numerically calculate limits at x approaching infinity. All right, so we need to have a couple of theorems to be able to do this. So let's think about what would happen if we have x to some positive power. Okay, so this is only true if x is a positive power. And we're saying what happens as x approaches infinity. Well, if x is going to infinity, if you're going to raise something infinite to an exponent, if you're going to square it, this is horrible notation here. We don't actually square a cube infinity, but this is how we think about it. Something going to infinity squared or cubed, these are just going to be even bigger than they were before, right? Okay, so this limit is going to be infinity. All right, so now it's a little bit different as we go to negative infinity. So as x goes to negative infinity, again, still talking about a positive integer up there, or a positive exponent. So now we're talking about negative infinity squared, negative infinity cubed. And again, this stuff that I'm writing over here on the right doesn't have any official meaning. It's just helping our brains think about it. Okay, in general, when we square something negative or raise it to the fourth, any even power, negative things, when you raise them to an even power, turn positive. So these will still be infinite, but they'll be positive infinite. The odd powers, if you cube something negative, it stays negative. So it's still going to be huge. It'll just be negative huge. Okay, so this one kind of has two answers. This is equal to infinity if n is even, and it's equal to negative infinity if n is odd. Okay, so if we keep these rules in mind, okay, right here, then we can answer pretty much any limit as x goes to infinity for polynomials. Okay, so let's do a couple of examples. Limits as x goes to positive negative infinity of a polynomial. Okay, so we'll start off with the limit, just as an example, x goes to negative infinity of x cubed plus 5. Okay, so we talked about what happens to the limit as x goes to negative infinity for, excuse me, x cubed. Okay, so we're taking something negative and raising it to the third power, but it's huge, so this is headed towards negative infinity. All right, so if you take something negatively infinite, huge, and you add 5 to it, you're not really making any headway there. Like a negative trillion plus 5 is not so much different from negative a trillion. Okay, so this is still just going to negative infinity. Okay, by and large, adding or subtracting numbers is not going to change what's going on with the x bit of your limit. Okay. All right, so let's try another one with polynomials. Let's say that we have the limit as x goes to infinity of x cubed minus x to the fourth. All right, so this one, we know that we're going to positive infinity. So these two things are doing pretty much the same thing, right? This thing is going to infinity, and this thing is going to infinity. Okay, so I'm going to put this in quotes here, kind of like I do our 0 over 0. Infinity minus infinity. Well, if it was 2 minus 2, we'd say 0. If it was 5 minus 5, we'd say 0. But infinity minus infinity is a little bit different. Because x to the fourth is, it's going towards infinity, but x to the fourth is usually bigger than x cubed. So maybe this isn't straightforward and equal to 0. Okay, so what we're going to do here is a little bit of factoring, just to kind of look at this in a separate way, in a different way. So I'm going to copy this limit. I'm going to factor out the x cubed. If I factor out an x cubed, I get a 1 for the first term, and then a minus x for my second term. So let's think about what these two terms are doing separately. Okay, so we know that as x goes to infinity, x cubed is going to infinity. We know that this x is going to infinity, right? Because x is going to infinity in this limit. All right, so this is, now we're going to think about this again. I'll put this in quotes. This is infinity times 1 minus infinity. Okay, and think of that 1 minus infinity, think of that as being negative infinity plus 1. Okay, something hugely negative plus 1. Again, this whole term here is going to go to negative infinity. That negative infinity is going to obliterate that little 1 at the beginning that you're tacking on. Okay, so this is equal to infinity times negative infinity. Okay, so you've got two infinitely huge things being multiplied now. One of them is positive and one is negative. Negative things times positive things equal negative things. It's going to be hugely infinite. Something huge times something else huge. It's going to be huge. The answer is negative infinity. So it turns out from the beginning that infinity minus infinity, x to the fourth is bigger enough than x cubed that it sort of, dominates that expression, heads towards negative infinity. Okay, so when you have infinity minus infinity, factoring is always a good idea to see if you can think about it in separate terms. Okay. All right, let's try one more limit as we go to infinity. This is not a polynomial. It's just something interesting to think about. If we take a trig function. Okay, so let's think about, we don't need Desmos to graph this one for us, right? We know what this graph looks like. This is sine wave. Kind of keeps doing this forever and ever in both directions, right? Wow, that was a horrible graph. Let's try that again. Okay, so we know that sine keeps going in both directions in this wave. All right, and when they're asking us to find the limit as x goes to infinity, they're saying, what's happening as we head out in this direction? Okay, well, we know that if it's equal to infinity, that was like that polynomial that was heading up or heading down towards positive or negative infinity. The rational functions, they had an answer like 2 if it was leveling out at 2. Okay, but this sine graph never makes up its mind. It's not going to infinity. It's not going to negative infinity. It's just going up and down and up and down. It can never make up its mind. Okay, so when you get something like this, it never makes up its mind as it goes out to infinity. It never settles down. We just say that this limit does not exist. Okay, so it's possible that these limits at infinity cannot exist. For all the trig functions that are periodic and repetitive like this, their limits at infinity don't exist. Okay. All right, so now you remember when I gave you that little theorem about x going to infinity, I said those exponents had to be positive, right? Because a different thing happens if you have something like this. Okay, so what if this would be the case of a negative exponent, like x to the minus third would be 1 over x to the third. Okay, so what if the x thing happens to be down in the denominator? Okay, so we know that this thing is going to infinity, right? We talked about that. X to the n is going to infinity. So what happens if you take something infinite and put it in the denominator underneath a number? Okay, so if you divide 1 by something huge, so think about your calculator. If you typed in 1 divided by a trillion, it would give you like 0.00000. You'd have a ton of zeros. This is essentially 0. Okay, if you're going to divide it by something infinitely huge, that 1 is going to be chopped into so many pieces that it may as well be 0. All right, and the same thing happens as x goes to negative infinity. All right, because we know that x to the n in the bottom, okay, that's either going to infinity or negative infinity, depending upon if it's an odd or an even exponent. But it doesn't really matter. If something infinite is hanging out in the denominator, then that's going to be equal to 0. All right, and this is going to help us to figure out our limits at infinity for rational functions. Okay, so let's take a rational function and see if we can figure out what the limit as x goes to infinity is. All right, so we're going to find the limit as x goes to infinity of 2 minus x over 3x plus 5. Okay, so if we just kind of think about what's happening to this function as x goes to infinity, let's think about the top and the bottom separately. 2 minus x, 2 minus infinity, that's kind of like that, minus infinity plus 2. Okay, that top is going to negative infinity, right? That x is going to sort of dominate the 2. And then down in the bottom, you know that your x is going to infinity. 3 times infinity is going to be infinity. Plus 5, that's just more, right? So we've got infinity on the bottom. All right, so I get negative infinity over infinity. And again, I'm going to put this in quotes, okay, because it's not actually a thing that's equal to anything in particular necessarily. All right, this is kind of like our 0 over 0. So infinity over infinity is like 0 over 0, which means that we need to use a trick. Okay, and our trick for infinity over infinity, and it can be plus or minus infinity, it doesn't really matter, the same trick works. We're going to divide the top and bottom, numerator and denominator, by the highest power of x from the denominator. Okay, not the biggest power of x that's in the whole function, but the biggest one in the denominator. Okay, so let's go back to this function. We got negative infinity over infinity. I have to rewrite that. So we got 2 minus x over 3x plus 5. Okay, so we got that was equal to negative infinity over infinity, and we know that's time for our trick. So I said the trick was going to be to divide by the highest power of x in the denominator, and that is this guy right here, x to the first. So I'm going to divide the top by x, and I'm going to divide the bottom by x. And since I'm doing the same thing on top as I am on bottom, that's not going to change the function. Okay, so you're going to kind of distribute that division to every term on top and bottom. And again, we're not going to change anything. It's just rewriting it in a way that helps our brains look at it. Okay, so I'm going to divide 2 by x. I'm going to divide x by x. So I'm creating a complex fraction in this kind of problem. I'm going to take 3x divided by x and 5 divided by x. Okay, so since I've divided everything on top and bottom by the same thing, I haven't changed the problem at all. All right, then I'm going to simplify. I know that I can cancel out these x's, and I can cancel out these x's. Okay, so I haven't changed my limit. I'm just rewriting it. I've got 2 over x minus 1, and then 3 plus 5 over x. Okay. And then we're going to think through what we just talked about on the previous slide. I did it with 1s. We've got 2s and 5s here. But this term right here, okay, I've got 2 divided by something going to infinity. So again, you're dividing 2 by a billion, a trillion, something enormous. Okay, so this is approaching 0. And again, this 5 over x, it's approaching 0 because x is getting huge, infinite. It's wiping that fraction out. All right. So if this is approaching 0 up top, I end up with 0 minus 1. On the bottom, I end up with 3 plus 0, and I get negative 1/3. All right. Excuse me. All right. So if I go over to Desmos and I graph, in fact, let's see if this thing will let me do that. All right, so if I'm going to go over to Desmos and clear out that function right there. All right, and let's just start with a blank one. All right, so I had 2 minus x divided by 3x plus 5. All right. And we said that as x goes to infinity, this was going to be approaching a y-coordinate of negative 1/3. Look at that. We found the asymptote. Okay. We found that horizontal asymptote that it's approaching. It also happens to do the same thing out at negative infinity. Most of them do. All right, so that's what that calculation just figured out for us. Rather than looking at it on the graph, we figured it out from calculating with the limit as x goes to infinity. All right. Okay, so let's try another one. We're going to try the same sort of trick. We're going to evaluate the limit. We'll do this one at negative infinity. Okay, I've got x squared minus 5x plus 2 on top. On bottom, I'm going to do x cubed minus 3x plus pi. Pi, where did that come from? All right, so let's see what's happening. Essentially what's going to happen when we plug in infinity, remember that the bigger powers of x sort of tend to dominate the smaller powers of x. So you've got something going to infinity up here and infinity down here. Right, so anytime you see this kind of thing, you know that you've got this infinity over infinity. It might be plus or minus infinity with negative. All right, but in any case, you don't really have to figure out whether it's plus or minus infinity because our trick is going to be the same. When you have something going to infinity on top and bottom, you're just going to divide by the highest power in the denominator. And it has to be the highest power in the denominator or else the trick does not get the job done. Okay, so we're going to divide everybody in this problem by x cubed. All right, so I'm going to divide, again, I'm going to create a whole bunch of little fractions here. I have x squared. I'm going to divide that by x cubed. I have 5x over x cubed. I've got 2 over x cubed. Everybody's getting an x cubed in their denominator. X cubed over x cubed minus 3x over x cubed plus pi. Pi is just a number, right? We can't be afraid of pi. It's just 3.14. It's going to behave pretty much the same way the 2 is up top. It's just a number. All right, now I'm going to go through and kind of reduce all of my powers of x. Okay, so I'll just do a little bit of algebra here. You've got an x squared and an x cubed. Okay, so that's going to leave you with x to the first on the bottom. So we're just going to go through and simplify all those fractions. And we haven't taken the limit yet, so I'm still copying this limit as x goes to negative infinity. So here's my big fraction. My first term is going to be 1 over x. My second term, 1x is going to cancel. I'm going to have squared on the bottom, so minus 5 over x squared. And then 2 over x cubed. Okay, so I'm just reducing all these fractions. On the bottom, I have x cubed over x cubed. It's going to be 1. Same thing for the x over x cubed. That's going to be 3 over x squared. And then our friend pi over x cubed. Okay. Anything that still has an x in the bottom, number over x, remember x is getting huge. It's getting hugely negative, but it's getting huge. Okay, so anything that's still got an x on the bottom is headed for 0. Okay, those x's going to negative infinity are going to wipe out those fractions. You're dividing 5 by something infinite, 3 by something infinite, 3.14 divided by something infinite. Everything in this entire problem just got wiped out to 0 as x went to infinity, or negative infinity. So I ended up with a whole lot of nothing up top. On bottom, I've got 1 minus 0 plus 0. Okay. And 0 can be on top of a fraction. Okay, 0 divided by 1, that's 0. Okay. So that limit is equal to 0. All right. So let's do one more of these rational functions. So we're going to do limit as x goes to infinity, 2x to the 4th minus 5x squared plus 6x plus 1 over x cubed minus 7. Okay. And again, you have some stuff going to infinity on top, stuff going to infinity on bottom. All right, so this is always going to be the trick. And again, who cares? It might be going to positive infinity, might be going to negative infinity. I don't even need to figure that out because this has just got that trick written all over it. And again, it's because it's infinity that we're doing this trick. Okay, the ones where we did factor and cancel in section 2.3, those were not going to infinity. All right, so again, you're going to divide by the highest power of x in the denominator. Okay, and for us, again, that's x cubed. There is an x to the fourth, but it's up top. So we're going to divide through by the highest power in the denominator. Otherwise, you're not going to get the right thing. Okay, so we divide everybody by x cubed. Okay, so I've recopied the entire rational function, but now I've got all my x cubes in the denominator. And anything, now we're going to reduce, so go through each fraction and reduce as much as you can. Okay, so 2x to the fourth over x cubed, that's going to leave me with a 2 and an x. The second fraction, I'm going to have one x left over in the denominator. The third one, I have a 6. It's going to leave me with an x squared. And then the last one is just 1 over x cubed. Then on the bottom, x cubed over x cubed and 7 over x cubed. There's nothing to reduce there. All right, and once you've reduced anything that has an x left over in the denominator is going to 0. Okay, this is why we use this trick. We like it. It wipes a lot of stuff out. So what I'm left with in this problem is a 2x on top and a 1 on bottom. Okay, so as x goes to infinity, 1 is just 1. But as x goes to infinity, 2x, 2 times infinity, that's going to infinity. Okay, so this one, you actually ended up with an infinite limit. Okay. So let's take this function over to Desmos and just graph it and see if this... So if I graph this function, this is the beast, 2x to the fourth minus 5x squared plus 6x plus 1 divided by x cubed minus 7. Okay, this is a weird function, but look, as x goes to infinity, this right half of the graph, it's trailing off to infinity no matter how far I travel on here. Okay, so that looks like we got the right answer, right? That's not flattening out like the other functions were, like flattening out at y equals 2 or y equals negative 1/3 or something like that. Okay. All right, so this is all we're going to do for x going to infinity. We've still got those vertical asymptote limits that are equal to infinity that we'll pick up in the next video.